Hello, in this presentation, I'm going to present our paper entitled Localization of a Nano-transmitter in a Diffusive Molecular Communication System with Multiple Fully Absorbing Receivers. My name is Fardad Vakilipur. I'm a PhD student at the Department of Electronic, Information and Bioengineering, Politecnico di Milano. In this work, we provide new results about localization of a pointwise transmitter in a molecular communication diffusive channel by means of a spherical array whose elements are fully absorbing receivers. The performance of two different spherical arrays is analyzed to estimate the position of the transmitter that differ in the configuration of the fully absorbing receivers on their surface. The proposed localization method relies on a model that has been recently developed to predict the temporal asymptotic cumulative number of molecules absorbed by each of the fully absorbing receivers. The approach first estimates the distance between the transmitter and the fully absorbing receivers, and then use them in a multilateration technique. One of the most promising applications of localization in telemedicine is targeted drug delivery, which is realized by means of nanorobots. Numerical results are used to demonstrate the accuracy of the proposed method. Before going into the detail and technicalities, let us have some fundamental discussion over the topic and the connection between nanomachine and telemedicine. Telemedicine defined as a practice of medicine using technology to deliver care at a distance. But what kind of technology? Does the technology remain the same throughout time? How can we make a step further and take advantage of technology in a revolutionary fashion? Through our lifespan, we have faced challenges, and as we evolve, the problems get more and more complicated. A good recent example is the COVID-19 that we all have faced recently, and we can see its consequences at the moment by gathering for this conference virtually. So, what is the solution? How can we prepare ourselves for future complex, unpredictable challenges? The solution is already given in the definition of the telemedicine. We need to keep up with the technology and define new policies subject to the requirements and our predictions. In the end, one can conclude that new challenges require new solutions. Nano and microtechnology, and essentially nanorobots, are one of the most recent technological topics that has drawn many attentions. Nanorobots are designed to do primary tasks such as sensing, actuation, and computation. However, to ensure their capability of accomplishing complex tasks, a cooperation, or better to say, a communication is necessary. Specifically, we need a communication among nanodevices. But should it follow the rules and physics of the current communication system? We all know that the size of the antenna has inverse relation with the frequency in electromagnetic-based communication. Moreover, hiring electromagnetic-based communication in the medium is almost impossible, especially for high frequency due to the absorption of the waves by particles in the medium. Then, what's the alternative solution to establish a communication among nanomachines in a biological environment such as our body? Molecular communication was proposed as the most reliable and feasible type of communication among the nanorobots due to its compatibility with biological environment and energy efficiency. A basic example can be a cell that plays the role of the transmitter in a communication system and releases some specific types of molecules that are the information signal and propagate through the space, which is a physical channel. Another cell that receives and detects the signaling molecules can play the role of the receiver. Generally, Physical communication methods can be seen as a spectrum between wave and particles propagation. Starting from only wave, electromagnetic and acoustic communication are possible types. In case of mixture of wave and particles, optical communication is a good example, and concerning only particle-based communication, molecular communication is the key. Molecular communication itself can be divided into different categories, from less spontaneous movements like walkway-based communication to more spontaneous movements such as diffusion-based communication. In this work, we are focused on diffusion-based communication, where the signaling particles are spread based on the Brownian motion. The idea of diffusion-based molecular communication is that the transmitter releases a given number of molecules. The signaling molecules propagate in the physical channel, and a portion of them arrive at the receiver. Here we assume the transmitter is of the impulsive type, meaning that it releases molecules in the medium instantaneously. Concerning the receivers, generally there are two types, passive and active receivers. Passive receivers do not have any interaction with the signaling molecules, meaning that the motion of the molecules, or equivalently, the concentration of the molecules in space, do not change if the passive receiver is present or not. A camera that just counts the number of information molecules in a certain area is a good example of passive receiver. On the other hand, active receivers interact with the signaling molecules through reaction or by absorption. Here we assume the receiver absorbs all the molecules that touch its surface and are stuck there. In the jargon of molecular communication, this is called a fully absorbing receiver. Hence, analyzing fully absorbing receivers requires an extra consideration on the boundary conditions of the diffusion equation. Here in this short video, on the right-hand side of the page, you can observe the diffusive propagation of the molecules from a pointwise impulsive transmitter. It can be seen that the absorbed molecules by the receiver turns red and stuck at their place right after they touch the surface of the receiver. In the end, we compare the cumulative number of absorbed molecules from the particle-based simulation, the blue curve, and the analytical solution from solving the diffusion equation with proper boundary and initial conditions, the red curve. The blue curve is only one trial, and due to stochasticity of the Brownian motion, it doesn't match with the analytical solution of the diffusion equation, which represents the expected cumulative number of absorbed molecules by the receiver. But if we run the particle-based simulation several times and take the average, we can observe a good match. Of course, the fully absorbing receivers are more realistic compared to passive or transparent receivers, and in case of multiple nanomachines, it is worth to investigate receivers' observation since they are more common in real scenarios. Please note that in case of fully absorbing receivers, their observations are coupled with each other because they are absorbing molecules, and it results in changing the molecule's movement or equivalently molecule's concentration in the environment. The fully absorbing characteristic somehow can result in blocking the arrival of molecules to the other receivers. This behavior can be interpreted as the release of negative molecules by the receivers, since the receivers are reducing the molecules from the environment. Consequently, to model the receiver's observation due to the aforementioned interactions, we must take into account their behavior by a system of equations where the receiver's observations are coupled. In this plot, you can see that we solved the system of equation for the case of two receivers. It is called a single input, two output, or a cytosystem, and showed the cumulative number of absorbed molecules by the green receiver at time equal to 2 seconds for different position of the red receivers. When red receiver is blocking the line of sight between the green receiver and the transmitter, when theta is equal to 0, the green receiver observation is at its lowest value, and when the red receiver is at theta equal to 180 degree, meaning that the red receiver is on the other side or right-hand side of the green receiver, the cumulative number of molecules absorbed by the green receiver is at its highest value. To verify our derivation, we did a particle-based simulation for the same configuration of the fully absorbing spherical receivers in the environment, and you can observe that the analytical blue curve matches with the results from particle-based simulation data. Note that this particle-based simulation data was averaged over 100 trials. Now that we have the time domain transient expression of the receiver's observation in terms of system of integral equations, let us make an attempt to obtain the asymptotic values. By applying the Laplace transform on the system of equation denoted in previous page by Revit, we can convert the integral of the system of equation in time domain into a matrix multiplication in S domain. Then we take advantage of the finite value theorem and obtain the temporal asymptotic value of the cumulative number of absorbed molecules by all receivers in the 3D unbounded space. As can be seen, in the end, the relation between cumulative number of absorbed molecules is obtained by a simple matrix multiplication. Vector n contains the cumulative number of absorbed molecules. Vector t consists of the inverse of the distances between each receiver and transmitter. And matrix R is dependent on the radius of the spherical receivers, the relative distance between the receivers, and the number of released molecules by the transmitter. Finally, the asymptotic value is just a scalar matrix multiplication, and from the cumulative number of absorbed molecules and the position of the receivers, their radius, and number of released molecules by the transmitter, one can obtain the distance between the transmitter and receivers. The power of this model is that it takes into account the interaction between the receivers only by a simple scalar matrix multiplication for asymptotical values, and allows us to determine the distances between the transmitter and receivers from the cumulative number of absorbed molecules. Let us have a brief review on some theory from geometry. Multilateration is the process of locating an object according to distance measurements. In practice, the measured distances are more than minimum required number, which is 4, to ensure the quality of estimation. Hence, it results in an overdetermined system of equation. By rearranging the multilateration equations and finding the least squares solution of the problem, we reach to this closed form expression whereby knowing the distances between the transmitter and receivers, in addition to the position of the receivers, we can estimate the position of the transmitter. On the right hand side, you can see the graphical representation of how multilateration works in three-dimensional space. In previous slide, we showed the relation between the asymptotic expected cumulative number of absorbed molecules by the receivers with their distances from the transmitter. In practice, the arrival of signaling molecules follows a binomial distribution, since we are talking about the absorption or not absorption of the molecules. However, working with binomial distribution is not easy theoretically, and one can approximate it with Poisson distribution when the number of released molecules is high and probability of arrival of molecules to the receiver is low. Finally, since the sum of Poisson random variable is still Poisson, we assume the receiver's observation in terms of cumulative number of absorbed molecules follows a Poisson distribution. Now, it is time to combine all that we have prepared up to this page. The role of estimating the position of the transmitter is crucial in communication systems. It can be used in practical applications, such as localizing the source of the signaling molecules, like finding the cancerous tissue by nanorobots. Another advantage of estimating the distances, it helps to understand the channel parameters in order to establish a better communication, which can be used for synchronization purposes. In this regard, for the first time in the literature of molecular communication, we propose an array of molecular communication with fully absorbing receivers that can estimate the position of the transmitter in a three-dimensional diffusion-based molecular communication channel, relying on the cumulative number of absorbed molecules by each receiver in a long temporal interval. We have proposed two different configurations of the receivers on the surface of the spherical array. Array U is the one which the receivers are distributed over the array as uniform as possible, while array M has higher concentration of the receivers on its top and bottom, as can be seen in the figure. In the end, it is time to see the results of our simulation based on our derived theory. Here we demonstrate the root mean squared error or RMSE of the estimated position of transmitter for both configuration of the arrays. The simulation parameters are described in the table. The first figure on the left shows the performance of the arrays when the transmitter is located at 30 micrometer from the center of the array. As you can see, by increasing the number of receivers, their corresponding RMSE lines have lower value. By increasing the number of released molecule by transmitter, the RMSE drops. This is equivalent to signal strength, which can be interpreted as the increase of signal strength improves the accuracy of estimation. Moreover, by increasing the distance between the transmitter and the receiver, the RMSE increases, meaning the estimation becomes difficult for the array, and we can observe this behavior by comparing the plots. The plot in the middle was simulated when the distance between transmitter and center of the array is 60 micrometer, and the one on the right corresponds to the distance of 90 micrometer. After seeing the general performance of the arrays to localize the transmitter, then what about the difference in performance of the arrays we introduced? Which array is better? Since the arrays do not have any prior knowledge about where the transmitter is located, we expect that the array with uniform distribution of the receivers on its surface performs better than the other one. And if we zoom in on the RMSE figures, we can notice that the RMSE corresponding to array U, the red line, is lower than ones from the array M, which is a blue line, in majority of conditions. There is only one exception, which happens when the distance between the array and the transmitter increases to 90 micrometer, and the number of receivers increases also. We can see that due to high concentration of the receivers on top of the array M, the directivity of the array outperforms the one we had for the array U. This behavior shows that the concept of directivity exists even for fully absorbing receivers on arrays in diffusive molecular communication system, and it is worth to investigate in future. Conclusively, we introduced a method for the localization of an impulsive pointwise transmitter based on the asymptotic cumulative number of molecules absorbed by multiple fully absorbing receivers in an unbounded three-dimensional diffusive molecular communication channel. The proposed approach relies on a model that describes the asymptotic multiple input, multiple output channel model in diffusive molecular communication system. After estimating the distance between the receivers and the transmitter, a multilateration technique was hired to estimate the exact position of the transmitter. Two different spherical arrays were considered that differ in the configuration of the receivers on their surface. A performance comparison of the two is done in terms of root mean squared error between the estimated position and true position of the transmitter. We showed that in case of having no prior knowledge about the position of the transmitter, the receiver's distribution on the array must be as uniform as possible. However, in case far distance estimation, when the number of receivers is sufficiently high, the array can take advantage of the directivity and it shows lower root mean squared error compared to that of uniformly distributed fully absorbing receivers on the surface. In future, we would like to demonstrate the directivity of the arrays with an arbitrary geometrical shape and configuration, and also work on the direction of arrival that arrays can have in the environment. In this work, we have made a strong assumption, which was knowing the number of molecules released by the transmitter. It would be good direction to relax this assumption and investigate what will happen if the receivers do not have any information about the number of released molecules by the transmitter. Going through the calculation of pseudo-inverse and its component is computationally demanding. Hence, finding a less computational costly algorithm to detect the position of the source would make us another step closer to practical implementations and reality. That was all about our recent work, and thank you for your attention.